Hi, how are
Hey,
you?
hey, how are you?
Thank you for coming.
Yeah, thank you for inviting me. Yes.
That's
So you
wonderful.
are, let me understand, you are among the, let's say, you contributed to create this app, to build this app.
Oh, no. The app
Oh, I see.
itself, no.
I see.
I created this club, the Science Society, but not the app itself. No.
Oh, I see. I see. I see.
Yeah, but yeah, thank you for coming.
Yeah, it's a
Um,
pleasure. It's a pleasure. Yeah, thank you for inviting us.
that,
Oh, okay. Somebody's joining.
Hi,
Yeah, I
Victoria.
should say because.
Hi, Dominic. I
Ah,
hope
Hello.
I
okay,
say
Dominic.
everyone's names right. Please correct me if I say it wrong.
Yeah.
So the history of Clubhouse, I don't know. It started during COVID times with
Mm-hmm.
like more famous people. Like they invited Elon Musk and a few
Oh,
famous tech people and also like musicians and so on. And it was invitation only back then. So my husband was on here quite early because he was working at Vice Media. I don't know if you know Vice Media from HBO, the news channel.
not really. Not really. Yeah.
Yeah, anyways, doesn't matter. And hi you Yon. Am I saying your name right? I'm sorry.
Julian. Julian.
Juyon. Okay. Oh, Dominic
Hello.
left. Oh no.
Oh,
Oh,
What happened?
uh-oh.
Dominic, come back up. I invited you to
Here,
speak.
I'll bring him.
Uh
Calling
yeah,
you
I
back.
hope you'll
There we go.
did okay, great.
Oh, okay, I can speak now. Cool.
Yes. Oh,
yeah.
yes. Oh, I didn't know you were having trouble.
Okay, yeah. Thanks.
Yeah. So, this app became quite popular quite fast. It was invitation only. So back in time, when I started inviting people, I had to ask for their cell phone number to send them an invite. So I felt like a spam or for
I see.
like somebody that's trying to rip somebody
I
off.
see.
But most people actually said okay pretty fast. Just some people ask, is it really necessary? And I said, I really apologize, but I have to send you an invite or you cannot speak here on Clubhouse. But
I
now it's
see.
better. Now it's everyone can just join. So,
Yes.
yeah. Anyways. Hi Jamie. Hi Frank. Hi Serena. Meet
Hello.
Dario, Yuan, and Dominic. How are you?
Hello.
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 Well, welcome. Welcome. We're so pleased to have you tonight.
Hello, welcome.
Yeah,
Hi,
we are very
Frank.
excited
Hi,
to have you
Serena.
here.
Jenna.
So we'll start in around 5 minutes, and if it's okay with you, we usually I'll introduce the three of you, and then Victoria usually asks like a more general question to you, like about like your general science interest career, if that's okay, and then the stage is yours to present your work, and then we'll take questions from the audience or
Sure.
whoever wants to
Well,
ask.
I don't know. I think Dominic and Julian will agree. I mean, if questions come during the presentation, it's probably even better in the sense that we feel, sometimes when you talk, you have the feeling that maybe other people are sleeping or, okay, no, having a feedback like during the talk is sometimes more interesting. So if people want to ask questions during the talk, it's even better.
Thank
Okay.
you, Dario. Another thing is that if you look in, there's the room chat, and sometimes people will use that room
Ah,
chat
I
and put
see.
questions or comments in there, and you can use it too.
Sure.
So
Okay.
that could also, that could be some engagement too and input.
Sure.
And thank you for that tip.
How has your Oh, it's early morning, right, for you right now?
Well, early morning. It's 10 a.m., depending a bit on
Oh,
the
it's
definition
10.
of early
Okay.
morning. Yeah.
It's okay.
Well, my
Sorry.
own definition is probably quite early, but okay, that is just my own definition.
Yeah. So your day just started basically, so that's nice. Li Xiu Cheng, she's in the audience. She will be our guest speaker soon. Nice to be here. Nice to meet you here. Nice to see you. I hope you'll enjoy the talk. She just joined Clubhouse for. She will give a talk about her paper in machine learning. It's quite exciting. So anyways, and thanks everyone in the audience for coming. We'll start in around 2 minutes. Oh yeah, and if you want to join us here, then please come to the stage. If you want to ask a question, please come. It's supposed to be interactive, so everyone, please come to the stage to ask questions. And we'll start in around 2 minutes.
So is this the first time all of you have been on Clubhouse? Was Katerina showing you the ropes of how it works? Doctors?
Yeah, it's my first time.
Yes, me too.
Cool. It's a surprisingly enjoyable sort of platform where everybody can relax and doesn't have to worry about how they look on camera, but everybody can still talk and engage in that way. It's always good fun. It also gives you a good a chance to learn a lot. I've actually learned a lot with Science Society in this the short month I've actually been here, and it's thanks to people like yourselves. That's why I'm super grateful every single time people like yourselves are able to come over and educate us. And plus, I love everything with the word quantum in it. Everything.
And I just went to the market. I just did a complete marketing in Clubhouse, and I bought 2 kinds of chocolate. So this is another bonus.
Really? I don't know you did. You can actually buy chocolate in here. I didn't know that. So do you have a busy day planned for yourselves after the talk today, doctors?
You're
Do you have
already
a
on the
busy day
hot
today?
seat.
Yeah. do you do you have a busy day today after the talk?
I have to think about what I want to do today. First.
Yeah.
Oh, to be determined then. To be
Yeah,
determined.
that's right.
That's a really good
There's
answer.
usually something to do.
Who said that? Dominic,
Well,
did you say that? Who just gave that answer? I have
Yeah.
to think. Because when people ask me, what have you got planned for today? Even if I have, a well-organized to-do list, I feel so tense, like I don't want to tell anybody, or I don't even want to, it's like
you don't want to
mental
commit.
labor to think of it, an answer. I like
Or
that
also
answer.
saying I don't know yet somehow feels like wrong for me. If someone asks me what you're going to do, and I don't know yet, saying I don't know somehow feels I've failed in my day.
You
I
could
I
see.
say
feel
that.
I feel compelled to say, "Oh, I will be doing this. I will do this and that and that." That way,
You
it'll
could
make me
say
sound productive.
You could say the waves are going to collapse any moment.
Ah, you know what? I love that response. I'm going to use that because that's a good physics one.
Yeah, it's better than none of your business. It's true. It's a good answer.
It's non-deterministic.
Okay, I think we can slowly start, and then people will come in a few minutes, but I think we can just start for now. Yeah, welcome everyone to the Science Society. It's another amazing evening with a whole group of guest speakers here today. We are very honored to have you here. And let me give you a little bit of background information about today's guest speakers. Dr. Dario Rosa, he is the senior researcher and the team leader at the Center of Theoretical Physics of Complex Systems and the Institute for Basic Science, IBS, in Korea. And he's a theoretical physicist currently working on quantum chaos, quantum many-body physics, and quantum thermodynamics mostly. He got his PhD degree in Milano, Bicocca. I'm sorry if I said that wrong.
Cocca.
Bicocca. I'm from Portugal. So bad. It's the only town I've ever been in Italy. I was in the Alps and in Milano, actually.
I see.
And in 2014, in string theory and quantum gravity. After that, he moved directly to Korea, where he was first a postdoc at the Seoul National University, Korea Institute for Advanced Studies, KIAS. And finally, he joined the IBS in 2021, where he's the leading of research group of quantum chaos in many body systems. He's also associate professor at the University of Science and Technology, UST, and in his free time, if he has some free time, he also enjoys video games and running. And we have also today as guest speaker Dominik Safranek. I hope I said that right. He was born in the Czech Republic. He did his PhD in Nottingham, UK, and Vienna, Austria. Then he did his postdoc in Santa Cruz, California. And right now he resides in South Korea as an independent researcher. And he studied and worked on a variety of topics, including interpretations of quantum mechanics, quantum meteorology, and Gaussian quantum states, and the concept of entropy and quantum batteries. That he loves deep discussions and sharing his knowledge. So you're perfect here in this club and on Clubhouse in general, I think. And he enjoys outdoor sports, dancing, playing the piano, and getting lost in music. And our third guest speaker, the first author of the paper, Yoo-yeon and Gyhm, he was born in Seoul, South Korea. He got his bachelor's degree in physics at the Seoul National University. He worked at the Institute of Basic Science as a research assistant, and now he is in a master course in Seoul National University. He worked on quantum batteries, especially the bound of the quantum advantage for power of quantum batteries. And now he is studying how to quantify entanglement to estimate the quantum advantage of quantum batteries and quantum meteorology. It's such a great honor to have here three amazing and interesting guest speakers. So we are very honored to having you. Thank you for taking the time.
So I guess I'm gonna start now.
Do you want to ask your general question, Victoria, first, or?
I would be happy to ask my general question. Sure. Yeah, all of you, and the initiative that you're here with all of your different angles that you have approached your work from. And so my general question is, did you always find yourself interested in science, or maybe you made a career change or even a change in interests, or if you were always interested in science, can you say when you noticed that in your life that science was going to be what you focused on? And then beyond that, if you can share what brought you to the work that you're doing today, what was the path that you followed? So thank you. We can maybe go in the same order that Katarina introduced you, if that's easy.
Okay, so I can start. So, well, it depends when you say always, but yeah, I started to be, let's say, to think of myself as a scientist around the end of the high school, I would say. Before I was fully focused on sport, let's say. Around the end of my high school, I started to be interested on science and on physics in particular, and I said, okay, let's try. At the time, I was still, let's say, putting more efforts in sports than in studying. But okay, let's say the moment in which I realized that I was a scientist was when I started the uni. I mean, I started, let's say, my bachelor degree, because at that time I didn't have time anymore to do sport, and I realized that I was enjoying more my life by doing science than doing sport. So that more or less the moment in which I fully realized that I wanted to be a scientist. Let's say that I mean, as Katarina said, my career has been a bit, in some sense, I mean, diversified, in the sense that I began my scientific activity as a researcher during the PhD, and at the time I was working on a completely different topic, string theory and quantum gravity. The turning point that eventually led me to this work came out during my second postdoc, so I would say 2016. At the time, I was still interested in quantum gravity, but I started to learn that quantum black holes are supposed to be highly chaotic objects. So again, with the idea of understanding better quantum gravity, I started to study quantum chaos and quantum many-body physics. And after a while, I start to, let's say, to realize that I was finding more, at least in my taste, more interesting questions in quantum chaos and quantum many-body physics directly, instead of in quantum gravity. So I switched my career to this topic around 2016 as a natural, let's say, continuation, essentially because I realized that I was enjoying more in studying directly quantum chaos rather than as an application to quantum gravity. I would say that's it. Then I got interested on how to come out with possible applications of quantum many-body physics, and that led me to quantum batteries. Yeah, I think I'm done.
Thank you. It's really fascinating. It's like, when you got a really good book in your hands and you just want to know what's going to happen next, because the research that you're all presenting is, we have great interest in it. We're really excited to hear what you have to say. And now we get to hear how you got there. So thank you. And
Thank
whoever is next, please.
Yeah, so I think I was scientist basically since I was born. Since I remember, I was watching documentaries and TV. I think the turning point was for me at the age of 11. I remember watching this documentary about special theory of relativity, and then completely got it, at least from the basic kind of point of view of an 11-year-old, and then
I find that of all the people that hear this question, everybody knows the answer. Nobody feels like they have to really search too hard. It's always right there. Thank you, Dominic. And next is Julian.
sorry.
Sorry if you weren't
No,
finished. I'm sorry.
yeah.
No, to me this is not finished. Yeah.
Yeah. Where did I stop? I think I muted myself.
I
Yes.
think so too. I thought, well, maybe, okay, short answer, okay. But no, please continue. Dominic.
Yeah, I'm not sure where I stopped. So
You mentioned high school, or yeah, you made one
oh yeah, no,
statement.
I did.
Yeah.
Okay, I see. Yeah, so I was basically a scientist from the very early age. I was always watching documentaries, but I think the turning point was when I was 11, and I watched this documentary about special theory of relativity. And I remember running to the kitchen and explaining her dilation of time and contraction of length. And she thought I'm making this up, but I wasn't. And at that point, I was just really interested in physics. Yeah, I also had kind of changes of topics in my life, not near as big as Dario, but also studied about 4 different topics. I think my main ones are the metrology, which is the science of measurement. So maybe you've heard about the detection of gravitational waves. So I am doing theory of that kind of measurements using like lasers and how to measure stuff. And then entropy. But this work is on quantum batteries, which is actually quite related to that. I think that's it.
Thank you. Thank you for finishing that.
Okay. I think my case is similar to Dominic. As I remember, I read I always read a book about the science, but I think that there is the important point for me because in Korea, the men have to go to military service, and I also did it. And then when I did the military service, I have a lot of time, but I couldn't do the study or the research on the science. So in that moment, I I had said, uh, I I think that I thought that yes, I'm person who really want to do to the study and the research on the science. So then after military service, I'm interested in the kind of the how to how to mm, how to manipulate the quantum state or quantum mechanics to apply to the technology. So it was very the great opportunity to me that uh, I could join the UST because the Dario did the how to say that the quantum thermodynamics and quantum batteries. It is very what I wanted to do. So I kept that my interest in science. Yes, thank you.
I appreciate your answer, and I feel like I'm speaking for all of us that we are.
I cannot hear anymore.
Uh-oh,
Sorry.
Victoria,
Yeah.
you're in the Matrix.
Very each other in your work. Yeah, go ahead. Oh, I got the
Yeah,
red bar.
it's okay.
Sorry.
But
It's okay. You
and
can
thank you
take it
for
over.
your wonderful answers and sharing this with us. I think it's always interesting for students and other people to hear about the pathway to science. So, yeah, thank you. And please feel free to start with the presentation. Thank you.
I'm going to start. So I believe you have the presentation opened. I think it's up there at the Google Drive. How this is going to work is I first present the first part, and Dario continues. Then I finish it off, and then it will be ready for discussions with Julian as well. And please feel free to stop me or Dario at any time to ask questions or Julian. And I hope you enjoy it. We decided to do maybe a little bit more general overview because just talking about our paper without the context would be quite boring. So we did general overview and then we have one slide about our result, but I think at that point you will be ready to kind of get it. So that's it. So if you open the presentation on slide 1, there's the title, which we call this quantum batteries and limits on charging. And I must say this work has been, the main engine of this work has been Gyhm, who is the student of ours. And thanks to him, we have this wonderful result. Slide 2, talk about a bit about outline of this talk. I will first talk about quantum technologies, because there where these works belong. A little bit about history, technologies that use some quantum effect, and then some technologies that are using the entire quantum potential. Then we switch to Dario. He will talk about batteries, galvanic batteries, quantum batteries, generally batteries. And afterwards, he'll talk about the advantage of quantum batteries compared to, let's say, all other type of batteries. Then he will talk about our results. And finally, I'll take over again and do the general thing again. And I think maybe you are interested. Okay, when will we see this thing in practice? So I provide some estimates and conclude the talk. It's aimed to be at about 20 minutes, so not too long, but not too short either. So you are not too tired to ask questions afterwards.
Thank you very much. That sounds great. I'm looking forward to this.
All right, me too. Slide 3. So quantum technologies. The first quantum experiment that was ever done was in 1887. That was about 30, maybe 40 years before invention of quantum physics, the theory of it. And it was done by Michelson and Morley. Maybe some of you heard of a Michelson experiment. And this experiment was aimed to study the properties of luminiferous ether. Basically, that's the stuff that was believed to carry the light as a waves, the same way as the water carries its waves. And the funny turn on this experiment is that it found that there isn't any, which provided one of the experimental proofs of special relativity and grounds for its derivation about 15 years later. Interestingly, at the time, they already knew that interferometry, which is adding of waves, works as well as for water, as in the left picture, as for light. So they already knew this kind of double slit experiment where you have two slits and you shine some light through it, you will get fringes. You've probably seen such experiment done with laser pointer or some laser light. You see these fringes. And this is exactly the reason why they thought there is some luminous ether, because as there is water with water waves, there should be something to carry the light. And why I say this is the first quantum technology experiment is because really with light, this is really quantum effect. Doesn't need to be explained by quantum physics, but it is a quantum effect. Slide 4. Then we go a little bit further. Year 1912, there's been first application of interference into crystallography. So that's a study of using these light waves, which X-ray is usually light wave as well, to study composition of materials, chemical structures, molecules, sizes of molecules. And there has been a gradual improvement on these methods, and today is routinely used in chemistry department. On the right, you can see the picture. This has been a wonderful method. It's been used to determine chemical structure of penicillin, so they knew that something works as antibiotics, but they didn't know its chemical structure. So by getting to know this, this led to discovery of other antibiotics. It also determined the structure of insulin, so they could mass produce and treat diabetes with it. The same method was used to discover DNA in 1953. And as I said today, it's routinely used. Another quantum technology that was invented was a transistor. So there was a time where the computers were really huge, basically something with a fraction of a power of your smartphone was filling out entire rooms. But with the invention of transistor, these computers got very miniaturized. Actually, nobody knew at the time when transistor was invented how it actually works, and that was determined only 10 years later using some advanced methods in quantum physics. So again, similar with crystallography, the explanation of how it works came later. So the experiments were in front of theory at the time. 1960, invention of laser. The method of this was known from Einstein already because that's the thing he got the Nobel Prize for. He got Nobel Prize for photo effect, and that's exactly what laser uses. It was quite difficult to invent it, but today we also use lasers routinely in, for example, playing CDs, Blu-rays. But so maybe not as common now. But it used to be in each of your computers. Funny thing, also one other quantum effects that we've been using to this day is effect called giant magnetoresistance. Maybe you remember a time around 1997 when our hard drives were 10 megabytes, so maybe 100 megabytes at most, and then suddenly it jumped to gigabytes. That was a huge jump, and that's exactly because they started using this quantum effect, which allows efficient storage. So these were the quantum technologies that are using just quantum effect. So these are not real quantum technologies in a sense that they did something that was done before, but just better, using some quantum effect that was explained later. But now on slide 5, we are getting to a thing what I call real quantum technologies. And those are the ones that are using the full quantum potential. And by that, I mean they are using quantum states that are designed and prepared to do something they want, together with the quantum effects like interference. And we already have some working technologies today. Some are the first that are already used in large numbers are the quantum sensors, one of which is gravitational wave interferometers. In about 2015, they detected the gravitational wave just for the first time. This experiment lasted about 70 years. So 70 years in making, they managed to detect these waves, which were predicted in 1916. So it was 99 years after they were predicted, they finally managed to measure it. And the way they did it, they started injecting quantum states of light. So not just the thing that comes out of your laser pointer, but something more complex, modified, using its quantum potential to the fullest effect. And this managed to improve the sensitivity in such a way that they detected the change in distance in about size 1/10 of a proton on the length of 4 kilometers. So that's really huge. It was a big discovery back then, and of course he got a Nobel Prize as a result for it in 2017. So you can see these things are becoming real now. Another real application is in quantum secure communication. These things are now used to transmits sensitive data between banks in Beijing and Shanghai, but I'm sure there are other applications where it can be used. Good thing about quantum physics and secure communication is that it's proven, as long as the laws of quantum physics hold, it's proven not to be breakable. You cannot break into a conversation without anybody noticing. And finally, maybe you've heard of quantum computers, which were conceived by Benioff and Feynman in 1981. On the picture below, you can see a picture of quantum computer and the main part of it, which is called superconducting qubit. 20 years later, after it was conceived, it was invented in 2001, and about 3 years ago, they managed to build it big enough and good enough that there was one very specific task, not very useful one, but a specific task when it seemed to outperform anything you can do on a classic computer. Any questions so far?
Yeah, please go ahead if you have questions. Slash your microphones. I'm good until now, but if you do have,
Okay, I'll just
I
go
was going to
for
ask, sorry, is
yeah.
you're talking about the quantum computers. That's something that they're working on a lot right now, right? Like, that's the kind of thing that'll revolutionize computers as we know it, right? All of the computers we've got right now will be completely like hackable, and they're going to seem slow and boring compared to that, aren't they?
Yes and no. So there are known tasks which nobody knows how to do efficiently on classical computer, which is, for example, factorizing large numbers. This factorizing large numbers is a quite important topic because that's how our secure communication works today. For example, when you communicate with a bank, it's based on factorizing some large numbers into prime numbers, like 21 is equal to 3 times 7. So those things can be done efficiently on a quantum computer. So basically, if you build a working example of this, you can break this secure code and break into banks. So that's one thing they could be efficient at. But generally, there are many things where it is known to be more. It is not known to be more efficient. So most likely, we will still use our computers today. But it's true there are some
Oh,
specific tasks that it's going to be better.
okay.
One other thing which I am most excited about, but for that you need a full working version of quantum computer, is chemical simulations, chemistry. So you can imagine we still have chemistry departments today. Why? That's because it's too difficult to simulate on a computer. When we build a quantum computer, this chemistry will potentially become obsolete because you can efficiently simulate chemical reactions. So you could run a million reactions each day instead of hiring PhD students in chemistry.
That's an incredibly exciting idea. Thank you very much for answering the question.
yeah, that's
Yeah.
where I wanted to introduce you to Lixue Cheng. She developed a new machine learning system to look for to work in chemistry and look for molecular properties. So she's here.
Oh,
Like,
awesome!
yeah.
Yeah. I've read some papers about that. It seems like it's working so well. Maybe so well to the extent it's almost dangerous in determining things that could help or harm. So I might be interested in that talk that comes after. Okay.
Please
So
continue.
there are no more. Yeah, I'll continue then. Slide 6. To explain the real quantum technology, let me talk a bit about qubit. So the real quantum technology uses interference, as we talked about, but this is combined with these quantum states. And what is a quantum state? I think the easiest way to explain it on a example of computer versus quantum computer is that computer uses bits, which is a unit of information, which has either 0 or 1. And this is what you can see in this first picture. We have 0 and 1. And we denote 0 by pointing the arrow up, and 1 pointing with the arrow to the right. And these are the only two options you have with classic computer. The quantum computer is somewhat special because you can have 0, 1, or anything in between. And that anything in between you can see on the middle right. And you can add this 0 plus 1 together and get something like 0.5, which is denoted by this arrow pointing in 45 degrees up. And this is using this quantum effect called superposition, which is basically the main engine behind interference. Interference is just superposition. And why is this useful? Is because by doing this you can explore a larger space that you couldn't with classical computer. So you can somehow get to know a little bit more in some specific topics than you could with classic computer, because when things are together, you can reach the conclusion faster. Which this is the main reason why quantum computers work better in certain tasks than classical ones. And maybe you've heard of entanglement. That's what Einstein called a spooky action at distance. And entanglement is nothing else than a superposition between joint states. So if you have 0, 0 bit and 1, 1 bit, and then you turn them into qubits, you can again add them together and you get 0, 0 plus 1, 1. Unfortunately, I cannot draw a picture of this because this is a really complex 4-dimensional object that lives in some mathematical structure. So I just took some picture from the internet to show what this means. So these are the quantum states, and the real quantum technology uses these quantum states together with interference and other quantum effects. And maybe here you have some questions for me, and if not, this is the part where Dario takes over. So any questions?
Okay, maybe not. So maybe I can start. So yeah, let's keep in mind this, especially this last slide, slide number 6, because we'll be, we'll come back in a moment. But now we take a break, and we go to describe what a battery is, because essentially our work was about quantum batteries. So Dominic explained what is quantum. Now let's explain what a battery is. Now, here we started with a very simple example. We took a mountain dam, and we claim that this is a battery. Okay, let's see why. So let's see the main ingredients that made a mountain dam a battery, and then we will see how to further generalize this idea. So what is the main point in this picture in the mountain? Well, water would like to fall down. Water doesn't want to stay there, would like to fall down. However, we put a dam and we keep the battery, we keep the water there. So we can say that the energy stored, because we know that when water falls, a turbine, okay, I'm not very good with pronunciations. Anyway, this spinning object, which is below, maybe we have a question. No. Okay. We start to spin, and by spinning, this will produce, for example, some electricity, so we'll produce some work. So the idea is that we have an energy stored in our dam, in our battery, because essentially water wants to fall down, and in falling down creates, converts, potential energy to kinetic energy, and this create the basis to make a work production. So a battery is essentially something where you store energy and you wait for the moment in which this energy is necessary. Now, the other main concept that I want to make clear is what charging a battery means. So charging a battery, essentially in this example, is the following. I mean, when the dam is empty, there is no energy because essentially there is no water that can fall down. So charging our battery means that we take from below. Okay, it's not what happened because typically water is coming from above, but okay. In this example, we think that we take water from below and we bring it up to the dam again. So this is charging the battery because we spend some energy, because of course bringing water up costs a lot of work to us. But we store this energy in the dam. So charging the battery means moving again water, in this case, from below, where water would like to stay, to a new state, let's say, which is at higher energy, because water doesn't want to stay there. But in this way, our let's say work of bringing the water there become a potential energy that can be stored and used later. So these are the two main concepts which I explained with this example. Now we go to slide number 8, and we can go to something a bit more technical, which use exactly the same, let's say, concepts, which is the galvanic battery, which I think was one of the first examples of batteries, chemical batteries that came out in history. So here in this picture, we have two different liquids. One is, okay, here there are people that probably are much more expert than me in chemistry, so they can say better things. But okay, we have a liquid in which there is some zinc material, and another liquid where there is Cu. Now, here what played the role of water in the previous slides this time are the electrons. The electrons would like to stay on Cu, but they are kept on the zinc. So they are here, but they would like to move. So again, with the previous example in mind, we can say that we have some energy stored because our electrons would like to move, and is ready to be released. Now, when we create the connections between the zinc and the Cu, let's say the electrons are free to flow and they want to do that, so they move to Cu, where they essentially take the Cu, the cations, the Cu plus, which are in the solution, and they make a reaction and they create Cu metallic, and at the same rate, some zinc, which is in the metallic bar, become a cation and go to the solution. So this is more or less the same that we saw above when water fall down. So this time these are the electrons that leave the zinc and move to the Cu. And in doing this process, they can, let's say, release their kinetic energy and, for example, create, light a lamp and something like that. So in this case, what does it mean recharging a battery? I don't think this kind of battery can be recharged, but okay, let's assume that it can be done. Recharging the battery will mean that we take again the electrons and we bring them back to the zinc bar. In this way, let's say we store again the energy, and our battery will be again charged. I apologize in advance if my explanation is super dumb, but okay. At least for our purposes, this is enough. And okay, so what is the general lesson that we can learn from these two slides? The general lesson is that a battery has some stuffs, which can be electrons in the case of the chemical, which can be water in the case of the dam, but there is some stuffs which is brought forcefully where this stuff doesn't want to stay. So in the case of the water is brought in the dam. In the case of electrons, they are brought to zinc, which is not their favorite friends. Now, the idea of quantum battery is essentially the same, in which now these stuffs are qubits. So let's go back to the idea that has been introduced by Dominic in his last slide, and we go to slide 9, where now we have our qubits that we know they can stay in two states. So let's say state up and state, let's say, right, or 0 and 1. And okay, so the first key ingredient in order to create a battery is to create a preferred direction, a preferred orientation. So what we have to do is to, let's say, convince our electrons to choose an orientation. And this can be done, for example, by a magnetic field. By creating a magnetic field, we can create a preferred orientation such that our qubits prefer to stay, for example, in the state up, which is the state 0. So this is the state in which they have no energy because they are, let's say, at the minimum of the energy that they can explore. On the other hand, when they are in the state 1, which is the state, let's say, in which the qubits are oriented along, towards right, they are charged because they don't want to stay in this position. They want to move to the 0 state, but they are forcefully took in that particular state. So charging our battery means that, let's say, without their intention, our qubits are brought to the state 1. So here we create energy, or let's say we put energy, we store energy into our battery, into our qubit, by force this qubit to stay in a state that it doesn't want it to stay. Now, so far, this, is using, let's say, a quantum idea because it's using qubit, but is exactly the same of our zinc or our water before. Essentially, we take something, we bring it to a state that it doesn't want to stay, and we store energy there. So far, no reasons to use any quantum technology. It's just a game. However, an advantage in using quantum states appears when we have not just one cell, which means one qubit, but we start to have more than one. So let's assume, for simplicity, that we have 2 qubits. Of course, exactly the same idea will apply for many more qubits, but let's focus for the moment on 2, which is by far simpler. So in this case, our low energy state, the discharged one in which the battery is not charged, is the state in which both the qubits this time are in the state 0. And it's not hard to, let's say, to understand that to charge our battery, we need to go to a state in which both are in the state 1. So here I'm denoting with 0, 0, let's say, the fully discharged state, and 1, 1, the fully charged state. So charging means going from one case to the other. So what we call quantum advantage essentially provide an answer to the following question: how fast we are in bringing our qubits from the state 0, 0 to the state 1, 1, and how fast we can do this process compared to a classical process. So the idea is that suppose that now, let's say, these qubits are charged, let's say they are brought from 0, 0 to 1, 1 via a classical technology. This can be done with a certain speed, and the speed can be measured. And then the question is, can we use some intrinsic quantum, let's say, feature? Can we make use of this fact that these are not bits, but they are qubits, in order to make use of the quantum part, in order to make this process of going from 0, 0 to 1, 1 faster? The answer is yes. And to understand why, let's first explain how these 2 qubits can be classically charged. And okay, classically we don't have many options. There are essentially just 2 options: parallel and serial. So parallel, the idea is that you have your 2 qubits that now I'm representing with these 2 rectangular shape. And okay, we take 2 chargers. So we connect 1 qubit, or let's say 1 battery, 1 cell, to 1 charger.
Sorry, I just want to add that this is slide 10.
Yeah, thanks. Yeah. I always forget to mention. Yeah, I'm going to slide 10. Yeah, thanks, Dominic. So on slide 10, we take these 2 qubits, these 2 rectangular shapes, and since we say, okay, we have 2 qubits, let's charge them independently. We charge one of them, and at the same time, we charge the second one. Now, of course, let's say the time to charge a qubit is the same of charging 2 qubits, because they are charged at the same time. So this is fine and actually convenient, but requires two chargers. So essentially we are, let's say, a little bit cheating because we are putting twice the efforts in doing the same job. So this is what is called parallel charging, in which essentially in order to charge fast, you need to increase the, let's say, the potentials that you need to play, you need to put in the game in order to charge. An alternative, which become slower, is the serial one. So in serial one, we have two cells, but we have just one charger, and so the only thing we can do is to charge one cell at a time. So we take, again, in the slide 10, we take the charger and we charge the first qubit. Once the first qubit is charged, we, let's say, detach the charger, we go to the second qubit, and we charge the second qubit. So if you do this process with one charger, we need twice the time, because we need to, let's say, charge twice. We need twice the time because you need a certain amount of time to charge the first qubit and then the same amount of time to charge the second qubit. This is the serial approach. And classically, there is no other way to charge. However, and here we go to slide 11, quantum charging, in a sense, is really a combination, a combo between parallel and serial. So at the quantum level, and this is the main idea, is that two qubits form a new entity. This is, let's say, this is really the moment in which entanglement and superposition are at work, and they collaborate to create the charging advantage. Let's try to understand this idea with the square that we draw on the left. So on the left, I'm putting on the four vertices of the square the possible four states that we can, let's say, explore classically. So there is the state 0, 0, which is our starting state. There is the state 0, 1, in which one qubit has been already charged, but the other no. Correspondingly, the state 1, 0, which is just the other way around. And finally, our target state, which is the state 1, 1. Now, if we want to stay with just one charger, we saw in previous slide, in slide 10, that the only thing we can do is to do a serial charging. So essentially what our, let's say, path in the space of states, classically, is that you go from 0, 0 to 0, 1, and then to 1, 1. Or alternatively, we go from 0, 0 to 1, 0, and then to 1, 1. So let's say with classical charging, the only thing we can do is to explore the boundary of this square, and we cannot do anything more. However, and this is the quantum magic, when we have quantum states and when we make use of quantum technology, or let's say quantum principles, these two qubits now form a new entity, and we have a plethora of states which lives inside the square, not just at the boundaries. And here we put an example, this state 0, 0 plus 1, 1, which is the entangled state that Dominic described in slide 6. This is a state which is absolutely non-classical. You cannot have anything similar classically. But these are states that at the quantum level are at disposal and they can be used. So pictorially, charging in the quantum way means that instead of exploring just the boundary of this square, you can explore the interior. And so you can travel from 0, 0 to 1, 1 via the diagonal instead of the perimeter. So you get an advantage, not because you are moving with larger speed. Larger speed would be the correspondence of the parallel charging, but this is a bit cheating in the sense that you need to put a larger potential. Instead, exactly with the same speed, you move from 0, 0 to 1, 1 via a shortest path, which can be, because we know that the diagonal of a square is shorter than the sum of, this is Pythagoras theorem, is shorter than the sum of the edges. So the real essence of quantum advantage is not that we go faster, but we are, let's say, our states are smarter and they can find better path to move from the initial state to the target state. Now, on the right of this slide, we draw this with a picture in which we have a table, which is our potential, our happy potential, U. And now, let's say we compare how we can do discharging at the quantum level above and at the classical level. At the quantum level, we have that all the qubits can simultaneously take energy from a single potential, and so we have a central state in which they are partially oriented. This is pictorially, I mean, it's not really, but okay, pictorially is the equivalent of 0, 0 plus 1, 1, and then they go directly to 1, 1, so to the final state. Instead, what we can do classically is just create a queue, and each qubit at once go to the table, get charged by our potential, and go. So the quantum advantage is really this collective effect, which is something that goes because we, by quantum properties, we have new states which develop a faster, let's say not a faster, a shortest path in the space of states. So now we go to slide 12, which is essentially what we did. So this was an idea that was already around in the literature. However, what we did is that we proved that the best possible advantage that you can get out of n qubits is n times faster. So if we have n qubits, via quantum methods, we can charge n times faster than with classical methods. So, to give an example, if we have a battery which is made by 10 cells, this battery charges 10 times faster, exactly with the same potential, just because it can explore better paths. So now let's go to numbers, such that we can probably understand better how far-reaching are the consequences of this result. Suppose that we have an electric vehicle. An electric vehicle that is about 200 cells. As far as I understand, for some Tesla, we arrive even to 7,200. But okay, let's stay with 200 cells. Good. That means that if we could use quantum technologies and we could replace these 200 cells with 200 quantum cells, this means that by quantum technology, we could get an advantage in the sense that the time to charge this battery made of 200 cells will be 200 times faster, which in numbers, it means that if we could make a quantum charging station, instead of 30 minutes to charge these 200 cells, we could take just 9 seconds. And if we could make our quantum charging process at home, we could pass from 10 hours to just 3 minutes. Something that is important, and it created some misconception when, let's say, not the paper, but let's say the press release came out. This is this will require a very different technologies. It's not a standard charging which you plug your car into the socket. Let's say, not the car, you plug, let's say, the battery into the socket. Will be a completely different technology, which definitely will require some time. But for the estimates of how much it will require, I leave the floor again to Dominic. Before that, if somebody wants to comment something, I'm happy. Otherwise, I leave Dominic to make a prediction of how much it will take to see this technology at work.
I just, yeah, go ahead, Jamie. Go ahead.
Oh, no, please, you go first, please.
I just wanted to comment that I'm really waiting for your technology, because
Hey, yeah, all of us.
because yeah, I have a Tesla and I live in New York City, so I always have to go to a garage to charge my car. It's so annoying. So
I see.
anyway, Jamie, go ahead.
I was going to ask, when you mentioned that this is going to be a very different type of technology,
Yes.
so it's not going to be like an upgrade or anything. Is
No.
this going to be similar to, like, maybe it's a bad example, but you know the old telephone booths that were put, payphones all over the country that was put so that people could call, but then when you got the cell phone, these things practically became obsolete overnight. Is it going to become like that? Is it going to make all this current technology for charging obsolete, or will it?
Eventually, probably yes. but this eventually could be probably long. So yes, but yes, the idea is a bit like that. I mean, let's say, I mean, I want to point out this because, for example, when the press release came out, we received some criticisms by saying, "Oh, but if you charge so fast, you will burn your charging station." The point is that we will not use the current technology, so we will not burn anything because we will not use the our technology. We will not exactly the fact that we will use the same potential is what we will prevent us to burn everything. It's a bit like currently with currently it is expected that with quantum computers we will be able to perform tasks that normally require years in just few seconds, and nobody currently object, oh, but this will burn the chip, simply because a quantum computer will be not based on chips. Here is more or less the same. When we will have quantum batteries at work, we will not use the current technology, and I agree with you that sooner or later will become obsolete, but maybe later. But okay, let's see what Dominic. Yeah, please.
Thank you. Thank you.
Yeah, but let's see what Dominic. What are? Yeah, Hans, do you want to ask something?
Yeah, so thank you very much. Fascinating topic. I just have a question regarding to the slide, um, specifically the slide explaining the quantum charging process.
Yes.
Slide, let's see,
Can
11.
you mute or you're
Oh,
kind
okay.
of a lot of
Sorry. Yeah,
noise?
noise.
Yeah.
Yeah,
Sorry, but if you
okay.
could
Sorry, hold
go
on a
to a
second.
quiet area, thanks. That'd be great.
Yeah, I'm in.
Yeah, maybe one possibility is that Hansen, you can write your question in the chat and we can comment on that, and then you can tell us if you are satisfied by the answer.
Okay, cool. Great.
I did have one before we go on to the predictions of when we get our hands on this technology. Um,
Yeah.
I'm trying to picture
Hmm.
an implementation of this, and so just so I understand, the advantage is realized because we're going to, you know, increase energy into many entangled states simultaneously,
Hmm. Yes.
and so by pushing, since they are entangled, that's the quantum trick here, is they're
Right.
entangled. So we can apply that potential to all of them simultaneously, and it's as a system it rotates in this quantum space uphill, and it recharges. So
Correct.
I'm trying to so there's a few questions about how that might work. I mean, there's for each of these cells there has to be a very large energy, or ideally a large energy difference in the state you're driving, the charged and discharged state. But then,
Yes. Go ahead.
so then, but you're gonna drop a potential across all of them at once.
Hmm.
So it's certainly not like the charging, cable that we have today, where
No.
we're gonna, yeah.
Absolutely. Absolutely.
So
Yeah.
I can imagine some, some chamber or something, but we're in essence, but it's because they're entangled. And the fact that they don't lose their entanglement on discharge, right?
Hmm.
They still stay,
Well,
or
they don't actually don't lose is a bit wrong. Let's say the initial state 0, 0 is not
hmm
entangled. The final state 1, 1 is not entangled. The entanglement is in between. So essentially, during the charging process, they become entangled. The
I
final
see.
state is not entangled anymore, and the
So
initial
you
state.
let them, yeah. So discharging lets them, dephase and become, disentangled. But the charging process is restores the entanglement.
Uh, in between, yes. Even the final state, let's say the final state, which is the charged one, because 1, 1 is the charged state, is not entangled anymore. Is a
I
product
see.
state.
I see. So
Is
it's only
really
the
in
path.
between. Is only
Okay.
the path. Yes, yes. Correct.
Interesting.
Let me also emphasize, but this is something that Dominic will explain a bit better. This is not only theory. I mean, elite. I mean, there are really few, probably just one experiment which realize in a lab this quantum advantage. So it's not only theory. He will probably say something a bit more about this, but let me say that there is, or at least one experiment in which this quantum advantage is observed and measured. Of course, there is a long path between an experiment and the actual technology. Let me go to Hans. Yeah, please.
If I can ask, do you have a reference or a link for that one experiment that you're alluding
Yes,
to?
sure. Let me. Okay, I could have. Okay, I will send them the chat such that everybody can see the experiment.
Great, thanks.
Of course, the paper is technical. I hope that I mean is a technical paper, but I think is decently readable. Let me also see. Okay, so Hansen is asking, can you explain the quantum charging process in details? The diagram shows the diagonal path from 00 to 11. It seems the classical parallel charging can achieve the same apparent path. Yes and no, can achieve exactly the final state, 1, 1. But the classical one just run over the boundary, over the perimeter. So it goes from 00 to 01 and then to 1, 1. So the final state is the same, but the length of this path is longer because, let's say, the sum of the two edges is longer than the diagonal. On the other hand, the quantum no, but what about parallel charging? Parallel charging is a bit different. Parallel charging will go from 00 to 1, 1, but let's say, how can I say, will not, let's say, it's not a fair comparison because you have to take two potentials to do that. So you are doubling, let's say, the potential. So you're not making a fair comparison because the quantum one is only using one potential. So I cannot draw on this on this picture, let's say, the parallel charging because this picture is assuming that both quantum and classical are using one potential. So this is an important point. I mean, to make a fair comparison, you need to be sure that the amount of energy that you put in the full process is the same in the two processes. So otherwise, you can always doubling the potential and get a better speed. But just let's say because you make faster your let's say you increase the speed, but this is what finally in the classical case will bring you to burn the charging station because you need to put an enormous amount of potential in order to be fast enough. Is it clear?
Dario, I have is my voice okay? Can you hear okay? Yeah, so I have a similar question with as Serena and also Hansen in the slides number 11, where you explain the charging process of the quantum
Yes.
charging. Okay,
Mm-hmm.
so that's exactly. I mean, I also perplexed. Might be, you know, I'm lacking some, you know, background
Yeah.
knowledge. The so the arrow you're pointing is a single qubit state, right? From, let me see, it's but when we entangle, we mean that we do two composite, like multiple, right? Say we entangle two qubits, and then I mean, if this quantum charging to go from the same water dam like energy levels, i.e., you know, you refer to the same potential, then somehow you have to decohere and make the say two qubits decohere as you were. I'm just because I think here if you draw, I would, you know, it will be clear to me if more if the end states is actually a now we have, say, without the external field, B field, that the so every state is well, it can just be any states, right? So equally likely. So now so now you have a preferential
Yes.
potential. Then after so I would imagine you take away that external potential, let it so in the classical case, then it just like thermal, it just drops to the temperature, right? So it becomes random. That's the end states, right? So what is the end states in your quantum charging? What's
Well,
the
in
end
both
state?
cases, the end state is the state 1-1, which is an eigenstate, which is again an eigenstate of the magnetic field, if you want, but it is an eigenstate with high energy. So the idea is that you pass from 0, which, to use technical terms, is the ground state, so it's a state without energy, and you bring it to the state 1-1, which is an eigenstate with high energy. So both are eigenstates. So in principle, I mean, if there are no dissipations and so on, both are states that are stable. The point is that the state 1-1 has larger energy because it's not an eigenstate, it's not the ground state. The idea is that in both cases, both classically or quantum, you go from 0 to 1-1. So the actual energy that you have in your battery at the end is exactly the same. But in the classical case, if you use just one charger, you have to pass through the perimeter. The other states are simply not there. They don't exist because they are states which are quantum. So you need a quantum operation to create these states. On the other hand, at the quantum level, you can create these intermediate states, so creates the entangled state 0 plus 1, and you can go to the state 1 via shortest path. I mean, going again to the to the battery, to the mountain dam example, is like that you want to bring your water from below to above, and you find a shortcut. You find a shortcut, a shortest path. Now, if you find this shortest path, you do exactly the same work, because in any case you have to go from, let's say, the valley to the mountain. But if you go exactly the same speed, you will take less time because the shortcut make a shortest path. Now, Hansen was asking the detail of the quantum charging, so I don't know how much in the detail I can go, but typically this. Okay, Ellie. Yeah, I will. When I finish my part, I will send the reference such that you can take it for the experiment. Now the detail, I don't know how much in technical I can do, but let's say that all this charging are done via let me be technical, via an external quench. So the idea is that you have your spin, your let's say qubits in a magnetic field, and at a certain moment you turn on a quench Hamiltonian, so a non-equilibrium Hamiltonian, and this Hamiltonian bring you from the state 0 to the state 1-1. Now, if this Hamiltonian is entangling, so creates entanglement, is an Hamiltonian in which, let's say, you have interaction terms between the two qubits. So these interaction terms create, during the charging process, states of the form 0 plus 1-1. I don't know if this makes sense to you, Hansen. I don't know how much familiar you are with quantum mechanics, but again, I can.
Yeah, no, I'm okay. Can you hear me? Is it noisy right now? I don't know if
Yeah.
can you? Yeah, I am a theoretical physicist. So I
Good, good,
guess
good.
yeah. So
So
the
okay, I can tell you the details. I mean, the classical
Um,
charging is done. Suppose that suppose
Dario,
that yeah,
I think they are getting quite long now. Maybe
right,
should I
yeah,
finish
actually,
my part and then we
right.
can discuss
I
the
agree. I agree.
mathematical details between two physicists?
Sure, sure, sure. Sorry. Yeah, please. Let's postpone this part and let's go to Dominic again.
Right, because I think that there's always some people leaving, so I just
Yeah.
maybe want to do the interesting part. Yeah, so let me go to slide number 13, because there will be some questions. Okay, how much is this real? We'll do a comparison with quantum computers, because really this quantum battery is to a classical computer sorry, this quantum battery is to a classical battery as the quantum computer is to a classical computer. So we can take a look at some timelines. The quantum computer was first conceived in 1981. The theory was done between 1980 to early 2000s. It's still continuing today, but the main issues are answered. And the first experiment was done in 2001. And outperformance of a classical computer was achieved 2019. So you can see there are about 20 years in between. Now, quantum batteries are much newer concepts, so they were first conceived in 2013, and the first experiment is just 7 years later by Kwak et al. And probably Dario will share the link. So now we can speculate on when we will reach the outperformance. As Dario mentioned, there is already proven charging advantage, so they already proven that this can be done. So as a proof of concept, it could charge faster than a classical battery, but there's maybe not really performance in like genuine comparison. So I would estimate maybe it takes another 7 years, since it took another 20 years when we have some reasonable advantage in charging speed. That's in a battery that's maybe somewhat comparable to a standard battery, and generally better maybe since this technology of quantum batteries will use very similar technology to quantum computers, and quantum computers are expected maybe to be generally better or widely used in 2040. The quantum battery maybe adds 7 years or a bit more, and we are getting to the year around 2050. So this is just about quantum technologies. Then on slide number 14, there's also a comparison with batteries. I'll skip through the history, but basically there is a long history of classical batteries. Just talk about the important stuff. So in a battery, to be competitive for battery, you need quantity which is called energy density, which means how much energy can you store in 1 kilogram. And the lead acid battery, which is the one that's used by combustion car, has about 0.11 megajoules per kilogram, while lithium ion batteries, which are in your Teslas, have about 7 times that. And in that 2020 experiment, the battery that they used was very similar to lead acid battery. So the orders are there. This is a great news because it means that this is not completely unrealistic technology, because it achieves similar energy density to other batteries. The trouble with that experiment is that it was done on a battery which weighted only 11 micrograms. So to scale it, you need to make it about 100 million times larger. This might be issue, maybe not such a big issue, but still, this putting into perspective, considering you need to consider scale plus a very different material, different charging. Maybe we are getting back to this year 2045, 2060. Also considering that you need the same technologies as with quantum computers. So slide 15, I'll skip that. Yeah, basically I would say maybe 2050, give or take about 10 years, is when we can expect a realistic quantum battery to be competitive on the market. In conclusion, on slide 16, quantum technologies are all around us. There are full quantum technologies already applied, which is gravitational wave detectors and secure communication, and maybe soonish we will see quantum computers too performing in some useful tasks. Quantum batteries use shortcuts in charging, so they charge faster with the same potential because they go through states that are not possible classically. The experimental proof of concept has been already done, but the practical thing we will see, in about 30 years, maybe a bit more. And I think that's it.
Yeah, thank you so much. for this wonderful presentation. I have a question for, like, the general audience. So what will the materials of the battery consist of, and will it help also additionally solving the issue of shortage of the current batteries? Because there are predictions that in, I don't know, the next 20 years we will run out of batteries even sooner if we all switch to electric vehicles.
Yeah, maybe I can answer that. So there is no shortage of lead and sulfuric acid, so we will not run out of batteries. The issue with technology today is that really electric vehicles need this high energy density, and those has been provided so far only by lithium-ion batteries. But one can expect maybe there will be some other types of materials that are being used. This is not a fundamental but rather a technical problem. As Dario mentioned, there has been many different types of batteries in practice. Especially this water dam type of battery is already employed in some areas. And lead acid batteries are used everywhere. Lithium-ion batteries is used only in those applications that really needs to save weight, because you cannot carry like a huge weight around when you're driving a car. Hopefully these issues will be solved at some point. I think this shortage is troubling in the way that we have a shortage because we don't know any other material that is competitive with such a high energy density. Now these quantum batteries use different materials, but maybe not so different. The experiment that I mentioned is they use some fluorescence molecule, which is it's some kind of a red dye actually. I don't know what it it's a very complex molecule. It's some dye, and they charge it with laser field basically. So the charging process is done through lasers, and lasers are kind of quantum, so that's where the quantum speedup is around. And you can see that this type of dye achieves the same energy density as the lead acid battery, but the future batteries will definitely use different technologies, because otherwise we will not solve the shortage. So this will have to be done both for standard batteries and for quantum batteries.
Just a quick follow-up. I think I understand better now. I'm looking at the diagram more. So, am I right that understanding that your system starts already with entangled states, say 0, 0? Is that correct? Just to confirm.
0, 0 is not entangled. So it starts from a state which is classical, let's say. It arrives to a state which is again classical. This is why you can do a fair comparison between classical and quantum, because the initial and the final state are both non-entangled. The point is that using quantum, you can pass through states which are inaccessible by any classical resource because they are entangled. Is it clear?
So this is where my confusion comes in, because I
Mm-hmm.
was thinking if you start with the entangled 0, 0, then you can go by phase operation into the 1, 1 by via just on the same block sphere. But now you're confirming my earlier question that your starting and end states are all classical.
Yeah.
That to me is, I have a hard time to understand. I guess I'm asking a similar question. Well, what is the exactly charging process? But you seem to have to entangle them first, and this become decohere that as well. So that's also operation that you change this energy of the entire system. I don't know how to compare the starting and the ending. Yeah. Anyway, so I guess
Well, of course,
Yeah.
you have to. Yeah, please, Dominic.
Yeah, maybe I can, because you answered already, so let me
Yes.
try. Yeah, so you start at this classical state, but it's not really classical. It lives in Hilbert space, which is
Oh, yeah.
it doesn't live in a classical space. You start from something you call classical, but it's not really classical. But then as you charge, then it becomes slightly entangled, then more entangled, then maximally entangled, then less entangled, then even less entangled, and then it's charged. So it goes through this process of starting not entangled, but quantum, then becomes more entangled as you charge because you are taking the shortcut through the non-classical states, and you end up non-entangled again. And this is done with lasers. People do it, for the last 30 years. So this is kind of standard thing to do.
So to follow up, so I get that the advantage is an entangled path between the two states, and you get a maximal efficiency there, or a minimum time, let's say. It would be reversible as well by the same principle, right? You could actually discharge in a much faster rate by this principle of the same factor, right?
Correct.
So you could
Yes,
have
exactly.
by choosing a quantumly entangled discharge pathway, you could unload all that energy in record time.
Correct.
Yeah. Although I would say the way how you unload the energy, because you need to put that energy somewhere. So if you are discharging through this entangled path, then whatever thing you're charging, it will become in a quantum state of superposed, not
Yes.
charged and completely charged at the same time, which is, for big systems, macroscopic, this is not going to happen because there will be a lot of,
Uncertainty.
lot of loss of,
Yeah.
So
leakage of quantumness outside. It's gonna destroy the quantumness.
so you can't return the path that you went. You can't
Oh
discharge in the
yeah,
same path.
No, you can. You can.
yeah, you can.
Uh-huh.
But if you want to charge something as big as a car, it's just not going to happen.
But definitely you can go down to the initial state. You can
Yeah.
choose. Let's say these operations. Again, to use a technical term, are unitaries. So they are all reversible. So you can always go back to the
Mm-hmm.
initial state. Then the way you could go back to the initial state following a different path, or that will depend. We didn't say anything about how to use this energy, so we didn't say anything about how to discharge your battery. But definitely, you are not forbidden to go back to the original state. So the full energy that you have in 1-1 is also can be used, let's say, in principle.
Fascinating. I'm sure somebody will think of an evil thing to do with that. But
By the way, I put in the chat the link. I don't know if you notice, but yeah, the link to the experimental paper is in the chat.
okay, great. Just technical question. From the diagram of the different states, the implication is for the number of qubits, it's, you would serially, you would take one step at a time. So it'd be at n times, whereas the diagonal in however many dimensions or qubit dimensional space, is the time that you're talking about the square root of n there?
No, unfortunately, the picture is just an
It's
analogy. I mean, the
it's
advantage
misleading.
is
Okay.
yes, it's a bit misleading. I know. We couldn't find any better way to give the idea, but yes, I agree. The advantage is not square root of n, is n. So technically, this is not really the full picture, but we didn't find any better way to deliver the message. But
Okay.
yes.
Okay. Thank you.
So, first of all, thank you so much for the great work that you shared with us. My question is about by considering the cavity charge protocol, which we know that it has a, explanation for the two-level systems, and is more practical and unconventional cavity charge protocol that we know about it. So I was just wondering, just turn that to the, synthetic biology and ask you, is that possible to use the same principle for the biomolecular machines? And also, can we use the distribution of the charge moves along the cavity axis or not?
I I don't really know. Maybe Dominic, you have something to say.
Yeah, I'm not sure if I understood everything because I had the trouble hearing, but um, yeah, you can use these quantum charges in molecular machines as long as they stay quantum. So for things to stay quantum, they really need to be isolated from environment. This is very difficult if that molecule is surrounded by some medium like water or anything else, because they'll be constantly bumping into some other things, and that will destroy the quantum properties. But yeah, I know there's been some discussions about the role of quantumness in biological systems. What was that? I don't know.
No, not
Hey,
sure.
what
Sorry.
about I think? Yeah, so I just thought that can be applicable in both free system and actually synthetic system. That's why I asked the question. And I mean, cavity charge protocol that I just talked about, it's very, I mean, high capacity of the energy storage. And I know that there was some application of that in the biomolecular machines. I was just wondering, maybe you had some ideas around that. That's why I asked that. Thank you, by the way.
Yeah, I don't know much about biological capacitors. That's that's not my expertise.
Yeah, for
Uh,
me it's the same. Yeah.
yeah, I think Frankie joined the stage. So, Frankie, do you have a question?
Hi. I joined late, so if my question is off topic, I apologize. But how small can fission be applied to this problem issue in the future, near future, or mid future, or long future? Um, because it seems so terribly efficient. Um, you know, storage is seems like it's going to be eternally a problem, and uh, but uh, you know, dividing atoms seems to be no problem at all as long as you can control it.
Mm.
Hmm. Yeah, I'm not sure if I exactly got it, but yeah, I can say some issues with these quantum batteries and compared to classical. So to get this advantage, first you need to create those highly entangled states. This is technically very difficult. So if you manage to entangle like only 2 qubits at the one time, you get double the charging speed. If you manage to do 3, you get triple. If you manage to do 100, you can get 100 times. But as more you entangle, more difficult it becomes. So I don't see a practical way how you could entangle maybe 100 of them at this point sensibly, maybe in future. But even if you get just 10 of them, then 10 times faster is pretty great. Now, the drawbacks of this technology is that, well, okay, so this is the kind of issue, but then it has the same drawbacks as any other batteries, and that's the energy density of a battery is not given by any quantumness. It's just given by the material that you use for building up the batteries. And the energy density is by far the main issues of today's batteries, also future batteries and all batteries to come, because you just need your battery to be extreme lightweight to carry enough energy. And this will not change with quantum batteries. So if you can charge lithium-ion batteries faster by quantum effects, that's great, but it's not gonna make the cars more efficient when they are running.
I think what I was kind of sort of pointing toward was if you had an unlimited number of charging stations based on, you know, micro fusion reactors, uh, uh, could could you could the problem go away effectively?
Yes, completely.
Could the efficiency of the battery go away? If that's diminishing returns with regard to the lithium ion or lithium polymer or whatever, um, could if you had a highly efficient number of charging stations everywhere that you just stop and go and stop and go and stop and go, um, and those stations were micronuclear uh, charging stations, wouldn't that or even or alternative solar or whatever,
Well, if
wouldn't that sort of solve the sort of practical problem that we have uh,
uh,
in the next dozen years or so?
um, well, I guess you can either carry that energy around, or you need to charge very often and not carry that energy. That's the same issue in any transport. I mean, Elon Musk with his rocket have exactly the same problem, right? That he needs to carry that energy around. I think if we have something like a fusion, you don't need to worry this problem at all. Just to give you some fair comparison, just in 1 kilogram of seawater, if you do the fusion on deuterium that's contained within it, you will get enough energy to power entire like my country, Czech Republic, 10 million people for a year. So 1 kilogram water you can power 10 million households for a year. So if you employ fusion in cars, you are done. You don't need to charge for a lifetime, or maybe several million of lifetimes. That's unlikely to happen though. I mean, anytime soon at least.
Yeah.
Yeah, definitely there could be you could have much smaller batteries carrying around, but then you need to charge very often, and I don't know how that would be done.
Just
I mean, people don't like it, right? So
No, you keep the battery size the same, but you just have recharging coils within the infrastructure, the roads and so on, like they're planning to do in some parts of Europe. So this accelerated charging would make, I guess, the recharging itself more quick, therefore somewhat more efficient in terms of at least time or productivity.
yeah, definitely. In that sense, I guess you could imagine having charging station in the road, and just as you pass through, it charges if it is like really fast. That would be cool. Yeah, I guess in a way you would make your car kind of a less efficient train now, just taking the energy as they go.
Yeah, in principle, you could bypass the problem of the energy density. If you are super fast in charging, you could
Yeah,
charge on the fly in some sense, right? I mean, so
yeah,
yes,
right.
in principle, yeah, you could bypass this problem by saying, "Oh, I charge on the fly using the quantum." So yes.
Yeah, but generally, I think there has been some ideas of just outsourcing your energy source, right? So that's the same again. Like I will talk about rockets because that's kind of a hot topic now. But so the rocket can either carry the energy in it, but then it needs to accelerate the fuel as well, which is a terrible idea. But the other idea is to not to have the energy source on the rocket, but have it on the ground, and just shoot a laser at the rocket and speed up that way. And that's much more efficient. And that's the same way that electric train works. That's the same way the hyperloop
Uh,
will
uh,
work.
try to. Oh, can you hear me? Is it still noisy?
Yeah.
Okay. So I just tried to get a kind of resource, kind of a quick search reviews that there's a paper sort of enhancing the charging power of batteries. Is that would be a good paper to look at the principle of the charging?
I wonder if this could generalize to the actual structure, for example, of a solar cell. So this kind of quantum entanglement that kind of boosts, I guess, the energy flux to some extent, or through some sort of weird lottery coordination. I wonder if the I guess the mechanism or the materials lend themselves to that translation.
Hmm. Ye- Yeah, so I don't know about the paper. Maybe Dario can answer that
Well,
question about
I
the
think
paper.
he's referring. I think Hansen. I'm not sure I understood, but I think he's referring to the famous paper by Campaioli et al. About where yes, I mean, if you want, if I understood properly, in this paper, Campaioli, Pollock, Binder, and collaborators, what they did has been essentially it was the first paper showing that by entangling operations, which are the one that we discussed, you can get an advantage. However, in that paper, if you want, in some sense, our paper is a proof of what they call conjecture. I don't remember the number. Conjecture 4. So, in some sense, in our paper, we proved what for them was a conjecture. So the best result of that paper was to show that there might be a quantum advantage, but somehow they were, in a sense, overestimating this advantage. They didn't find a tight bound. So what we did was to find a better bound to the charging power, and more in details, we found that among two sources of possible quantum advantages that they found, just one of them is relevant, the other is irrelevant. But yes, that paper is in some sense the paper that started this idea. So yes.
Mm-hmm.
Gotcha,
So,
gotcha. Thank you very much. And yeah, I'll get your paper
Yeah,
later.
thanks.
so to answer Ayel's question, yeah, I'm not sure about increasing flux would help solar cells. I think in solar cells, what's the main kind of a goal is to increase efficiency, because there's a limited energy in each photon that hits the solar cells, and the holy grail of solar cells is to reach as high efficiency as photosynthesis, which is about, I think, 87%. I think today's cells at best have about 40% efficiency, which is not bad, but could be better. If you get 87, then that's gonna be great, but I'm not sure how like flux or speed with which these photons are absorbed is going to help. I'm not sure that how that process would help anything.
I believe Abyss. Hi, Abyss. You joined us. Please go ahead and ask your question.
Thanks, Garrett. Hi, Dario, Dominic, and Juyun. Hope I pronounced your name correctly. So, yeah, I've been listening in the background. Great work, really promising stuff. I do have one question, which is kind of based off of what Serena was asking, which is like, you said that when in charging, it goes from a 0 state to a 1 state, which are essentially non-entangled states. I'm curious, is there some kind of thermodynamic effect considered in order to achieve the intermediate entangled state? By that I mean, um, in quantum computers, or at least like in some paradigms of quantum computers, there is, I mean, the system has to be cooled to near zero Kelvin to achieve an entangled state, or at least like prolonged entangled state. So I'm just wondering if this intermediate transition state, where the system is actually charging, like I said, from 0 state to 1 state, would require some kind of uh, thermodynamic consideration in order to achieve maximum entanglement. Thank you.
Oh. Well, the short answer is that in paper we didn't consider um, this effect. Actually, if you want, we just, I mean, yeah, we just said what is the best possible power that you can get. In all, let's say, our understanding, this requires some entangled state in between, but actually we didn't study specifically which states are required. This is something that Julian is studying more specifically recently, so is focusing mostly on how the states which give the maximal power must look like. I would say that what you refer is mostly, at least from what I understood, is mostly a technological problem nowadays, how to build such an entangled state. And I don't know much on that. Maybe Dominic is our, let's say, local expert on technology, so maybe he can add something.
Yeah, you are right. In quantum computers, they need to cool them down so they can achieve this highly entangled state. And the reason for it is that if you have things cooled down, they do not emit light, and they're kind of isolated. So the trouble with not having cooled down, it just emits a light, and that light carries some information, and that if that information leaks, then the quantum state is destroyed. And if you have a bigger entanglement, then it's much more likely to emit a photon and then destroy the entanglement. So there needs to be similar effects taking place in these quantum batteries. I'm not sure if cooling down is the only source. Basically, as long as you manage to isolate it from the outside environment while it is charging, that's good enough.
Yeah.
Cooling down is maybe one way. Another way could be work in some state that just doesn't communicate with outside world. So there's an idea of topological quantum computing where some states are protected, meaning that they are really unlikely to emit anything that leaks the information out. So as long as you do your charging in those states that are highly isolated, then you are fine. Not necessarily low temperatures are required.
So maybe, Dominic, we can summarize by saying that all the problem of the coherence that people study in quantum computing, it will apply also here, and the solutions that will work in quantum computing will work also here.
Exactly.
Okay.
Yeah, right.
So this is the where my previous confusion still lies. The when maybe it's a semantic or terminology when you use classical states. So I mean the technology so far is mostly very low temperature to operate qubits, right? So there has, I mean, the proximity probably not necessary. You can use laser to do the entanglements, but still, if it's to in that scenario, in order to say quote unquote classical, that means the two qubits are not entangled, right? To
Yes.
begin with, or right.
Yes. By
So
classical, I
then
mean, yeah. I means that they are in a product state.
right.
Yeah.
So you should
Sorry, Frank. Do you want to finish?
then the I would imagine the next step you have to entangle them,
Correct.
the two, right?
Correct.
And then in this process you're actually changing the entire quantum system, right? The say the number of microstates, I mean, for two isolated qubits versus entangled qubits.
Yes, I think so.
Then I mean, it's hard to say, how, I mean, how much energy that you need to, I mean, take you to. I think with a well-defined quantum system, we know that the quantum states, right? So say hydrogen, the electron, hydrogen atom that we know is n square, 1/n squared, so this can interact with lights. But now for your classical states, it can be the location, that can be known precisely, right? So then only when they become entangled, they become a two qubits quantum system. So that I mean the quantum states are different now. So now it depends on where you start as your low energy battery, state, right? So the bottom, the dam, the question changes. So that's my original question.
I lost.
Okay, I'll
Hello?
yeah.
Yeah, maybe I can add to that.
Yeah,
Yeah,
please.
it's true that it's classical in the beginning, somewhat classical, and somewhat classical in the end. In between, that's where the entanglement comes, and that's where you really need to protect it from this decoherence. You don't care about the beginning or the end, because if you have decoherence at the very beginning, you don't lose anything because nothing carries energy. If you have it at the end, you lose at the most 1 qubit, so 1 pieces of energy. But if you would lose it in the middle, you lose all of them because it's entangled state. So if one falls, all of them fall.
Yeah.
Why it's really sensitive to the coherence at that charging stage, but not at the beginning and the end.
Yeah.
Yeah. Also, to correct one of your statements, you said the technology today is always, called qubits. That's actually not technically true. The technology that Google and IBM uses, which use superconducting qubits, yes, that's very cold. Then there are some atom traps, which are also very cold. Those are the technologies used in Innsbruck in Austria. But for example, in Waterloo, Canada, there is a startup working with states of light. So you can do quantum computing with photons, and those are terrible as batteries, right? Because they fly around, but those are just room temperature, because photons do not interact very well with anything apart from matter. They fly through air without interacting with anything. So those photons actually are room temperature and it doesn't destroy anything because they barely interact. So that's the extreme. So not everything is cold temperature, but I guess the thing that we could use for quantum batteries are still just low temperature. So you are right in that.
Well, actually, I mean, you can, for photons, I think you can constrain them in a cavity, right? A cavity QED is something actually even old. So, I mean, I think technically you could. I mean, recently we came out with a paper about using micromasers as a quantum battery. So I don't know. I think who is this startup that you mentioned? Xanadu or no?
Yeah, Xanadu is one of them. There
I
are
see.
more.
I see. Okay.
The one I mentioned is Xanadu. That's in the one in Canada.
I
But
see.
yeah, there are more.
I see. I see.
I think there is one in Silicon Valley as well,
Mm-hmm.
using these
One in
photons.
Australia with Germany. Is that with Germany together that is working on a room temperature quantum computer that is quite small, so people could have it at home. That's their goal, at least.
Mm-hmm.
Oh, really? I didn't know that.
Yeah, thank you, very much. And yeah, I mean, don't take my, I mean, I'm here to learn, right? So from a layperson perspective, yeah, and thank you for correcting me on the temperature. Yeah, I'll Google more for the high temperature qubits. I mean, I know that they use the circular polarization as 0 and 1s. Yeah, thank you.
Actually, that was one of the reasons that I asked about the cavity charge protocol at the beginning. So, by the way, Dominic, I have one question. When you talk about isolated, it means no energy fluctuation or changing on the geometry.
Isolated means actually there is no information leakage from the system. Doesn't have anything to do with fluctuations, as long as they stay in the system. So what I mean by isolate is that black body radiation. Basically, if you heat up your stove, it turns red. Or you see coal burning, it's also red or yellow or some color. So it emits light, and this is what you want to prevent. You want to prevent your battery to emit anything. because as soon as it emits, it destroys the quantum states. So isolated means that the information stays in. The same thing you also want to prevent things being emitted at that. So you don't want to shine any light on it from outside source, because that would also destroy the quantum state.
It's like a Faraday cage just for photons or for lights. Basically, if you want to, if you know what a Faraday cage is. I posted the link of the company's news about the company name is Quantum Brilliance. It's between Australia and Germany.
Thanks.
Well, we talked for 2 hours. Thank you so much. I wanted to give you a chance to leave us because 2 hours of your time. You're always welcome back. This was a great honor to have you and the whole group. This was really a lot of fun, and thank you for answering so many questions and for this really great presentation that I think was really, you really did a wonderful job at explaining this in a way that everyone, even myself, can understand it. So thank you so much for that.
Thank you
Oh,
very
thank
much.
you so much for your interest
Thank
and
you.
your questions.
Yes.
It's been a wonderful discussion.
Yeah. Thank you very
I'll
much.
be happy to come again. Yeah, it
Yeah,
was
please,
awesome.
and join us when we have your guest speakers here, and join us again with updates on your work or maybe on other topics. You do so many interesting projects, so if you
Very
want
much.
to about another projects, please come back. We are always happy to learn from you.
Sure.
Awesome. Yeah.
And thank you everyone for coming and asking great questions and for learning with us here today. And please join the club Science Society if you like rooms like this. We will have tomorrow at the same time Dr. Brady from Australia. He will talk about his new junk DNA research and how we can use it to control fear. And then we will have on Thursday at noon from Europe Dr. Behla Vanidis talking about how human vision reconstructs time and perceives time very differently. We kind of know that we do that, but he found the mechanisms in the brain and showed how the brain does that. And on Friday, we will have astrophysicist from Max Planck Institute in Germany, Krasno Kutsky, about building blocks of life that form on space dust, how peptides form on space dust. So this is a room about the origins of life, basically, which is really interesting. And yeah, we will have more rooms also next week. We will actually have a nuclear fusion room where the CERN from Switzerland scientists collaborated with DeepMind and to control the plasma on fusion with AI in May. So maybe you will be interested in joining. And yeah, thank you so much for this amazing room. We really appreciate it. And enjoy the rest of your day. And if you're here in the US, good night for you. And yeah, thank you, everyone.
Thank
Thank
you so
you.
much, doctors. That was
Thank you.
incredible talk.
Thank
Thank you.
you.
Yeah.
Thanks.
And you
Thank
can
you.
Thank
also,
you.
Thank you
Thank
so
you.
much.
let me just add, you can also find our emails online. So drop us a question if you have any.
Sure.
Ooh, thank you
Sure.
so much.
Yeah, I really appreciate it. I will, I'll, send you questions.
Thank you for being so generous with your time and information. That's really exciting. And thank you, friends in the audience, for being here. It was great to be able to have such a wonderful audience for our presenters. So good night, everyone.
Yes, really appreciate it. Good night.
Looking forward
Good night.
to
Good night.
your
Bye,
next
everyone.
share. Thanks. Hope you come back.
Good night, everyone.
Thank
Bye.
you.
Bye bye.